Okay, here we are once again. It's the physics video lecture, psci 168, video lecture 28. So let's begin. We're about to start talking about heat engines. So what I'm going to do is some review of thermal physics and then segue into the heat engines. So today we'll say thermal physics to heat engines. Thermal physics to heat engines. So we have the basic law of thermal physics is that energy flows from the higher to the lower temperature object. Okay, and there's already a lot in here because we know temperature, say degrees Celsius or Kelvin. Those are the two scales that we use, and that goes back to thermal expansion on the one hand. On the other hand, this Q here, which represents thermal energy, also represents energy per se, energy in general. And so we could call this heat of combustion as an example. And if we burn some fuel, it releases heat. And in that case, maybe I could even draw our cartoon here. We've got the butter candle, and it's heating water in a beaker. The beaker's on a stand, and there's a thermometer in there. Okay, that reminds us of that. And that even reminds us of the definition of the calorie. So we had the whole thermal physics business, but then after we figured all this out in terms of the calorie, temperature, we had the really important law referred to as the mechanical equivalent of heat. Okay. The mechanical equivalent of heat. Can't stress this one enough. We'll definitely put this on the final exam. And all that it means. So we've got this 1 calorie equals 4,186 joules. The left side was the entire phenomenology that started the whole subject off. The right side was that this could be equated to a certain amount of joules, which we know is work. Okay, energy in the sense of work. Okay. And if we had an equality here, practically speaking, we always had this direction. So for example, we could work with friction, so force of friction, force times, well, I'm just going to write friction, keep it simple. So we do some mechanical work, but it involves friction and heat is produced. Or, and this was kind of an interesting one, we could have kinetic energy, 1/2 mv squared, a collision, a bullet strikes a metal plate, and the temperature increases and it melts. Okay. So kinetic energy to heat in that regard. We talked about the asteroid collision. Okay. That was kinetic energy and then made a big crater in the ground. And, hot explosion. Okay, so this is the direction we've had up until now. What we want, though, is to take a certain amount of fuel and get useful work out of it. So what we want is the other arrow in this equal sign. Okay. So next we want this direction. We want to have heat or thermal energy. And we want to get, I'll say, useful work out of it. And this mechanical equivalent of heat does tell us something, okay? I like that number, by the way, 4186. I always refer it to my stair climb. So we'll do the stair climb again right now. So we climb the stairs. Climb the stairs. We know that the work is mgh. It's our weight times the height. And just to put some approximate numbers in, if the weight is 800 newtons and the height is 5 meters, then that's 4,000 joules. So a good hefty stair climb, that's 4,000 joules, and that's approximately 1 calorie. Okay, but we're not going to talk about 1 food calorie somehow powering our own bodies up the stairs. But suppose we wanted to lift a mass of ours, equal to our own mass, wanted to lift it up the stairs. We want to get a machine to do it for us. Okay. Then a calorie would just be a little speck of fuel. Okay. And so we would have the fuel, and we have to come up with some mechanism that turns that thermal energy by burning the fuel into useful work. Okay. So can we, here's the question. Can we have or find or invent can we use a mechanism to convert thermal energy into work? And of course, we have such mechanisms, and our civilization runs with them. So we're going to go through it systematically, though, because there's a lot of interesting stuff along the way. And that mechanism, which is going to convert thermal energy to work, is the heat engine. The heat engine. I'm going to bring some little interesting model heat engines and demonstrate them next time. Right now I'm just going to describe their functioning. Okay, so that's what a heat engine is. It's something to take thermal energy and convert it to useful work. Now it does not have to be fuel per se. Okay, we'll learn later that there's other forms of thermal energy that can be converted to useful work. And that's why we're going to study this universal idea of the heat engine and not just the particular one. But we'll start out with some specific heat engines, analyze them, come up with the universal idea, and then analyze it. Okay, and as always, you're going to be able to find great pictures of this stuff to use to illustrate your book, your notebook. So that's the background on what we're doing. And like I said, it goes back to this mechanical equivalent of heat. And that's a fair amount of work. You know, a stair climb, a little speck of fuel, if we could get a machine to do that. Okay. Now I should, before I go on, our body does this work on a little speck of fuel, but it's not a heat engine. It's actually it's a chemical process. So it is an engine of sorts, but it's not a heat engine. And we'll see the difference as we work our way through this. Okay, so examples of heat engines. first one, I'll show you a working model, but you guys can look this up and get nice pictures of this as well. The first one just burns candles, and it's called the Christmas pyramid. And the functioning of the Christmas pyramid is the following. You have candles, okay, and I'll just draw 2 candles here. Okay, they're on a stand. And mounted here is a turbine. Okay. Turbine on an axle, and the fuel is burned right here, the candles, with a little different color. Candles burn and heat up the air around here, and the warm air rises, and you get it's a convection current, transfer of heat by convection, but you have the warm air rising, so you actually have a breeze or a current, an air current, and this turbine will then spin. So that's how simple it is. That counts as a heat engine. But we'll do a little more detailed analysis of it. And yeah, images of this, these are good. You're gonna know what you want to have for Christmas. They're ornate. Okay, it's an interesting thing, and there's a little various nativity scenes and so forth and so on. Okay, but the point is that it rotates and can be said to do useful work. You can hook something up to it and have it do some useful work. So we burn fuel. The candle is fuel, as we know. And then we heat the air. The hot air rises because it's less dense, so we have a convection current. Convection current, or heat transfer. Convection currents because the heated air rises. Maybe some air rising like this, and that turns, that spins the turbine. Okay, so 4th point, turbine spins, and if it's connected to something, does work. So interestingly, this Christmas pyramid has all the ingredients we need to talk about heat engines. And it's a charming thing as well. What I'm going to demonstrate next time is that when you put a chimney on it, you increase its efficiency substantially. Okay, so I'll just continue that list with an important note. So 1, 2, 3, 4, 5. A chimney increases the efficiency. And that's also part of the analysis to come. So yeah, if I can get that to work next time, you put a chimney on this device and it spins much more rapidly. So there's no doubt that the chimney really increases the efficiency. And then later on we'll see why that's the case. Okay, the chimney effect is important. So that's the one engine that we're going to analyze. And the second one is just a steam engine. And we also have a small model that I'll demonstrate for you guys. Talk a bit about it. But the principle of the steam engine is that there's a boiler. Okay, that's a tank. In ours, it's got a window in it, and the boiler has a little water inside. Okay. And we put a fire. So we have fuel. I should say fuel. So we have fuel and a fire. Heating the water in the boiler, producing steam under pressure. And if you can take that steam under pressure to a cylinder with a piston in it, and that piston's connected to a flywheel, and then you can get this flywheel to rotate. So this I'm also going to bring to class to show you guys. So the steam pressure pushes the piston forward and causes the flywheel to rotate. And again, it's hooked up to something, it can do work. You even see the work right here, because the work is equal to the force times the displacement, and the pressure times the area gives you a force, okay? So again, fuel and fire on one end, thermal energy, steam, piston pushes forward, you get work over here. Now if you look at this, you realize, well, that's only 1/2 turn of work, and then I have to get this thing to go back again. So what you need is a valve to release pressure and turn the process into a cyclic one. So valve to release pressure. And so what do we have here? We have fire and fuel, we have steam under pressure, we have work. So what else we have for your vocabularies here? We have the cylinder, we have the piston, we have a connecting rod. There's a connecting rod. And we have a flywheel. Okay. So I'll bring one of these to class and we'll discuss it at greater length as well. These are the two objects that I'm going to demonstrate to you, and out of the demonstration and the analysis of this, we will derive or develop the universal heat engine idea and its efficiency. So that's where we're headed. So if you can get images of this here and some steam engine images and schematics as well, put those in your book. I think that's where I'm going to leave it for today, okay? So yeah, right now I don't have any calculation type of thing. We're just gonna leave it at this. I'm gonna come in, we can try to get the demonstrations for these, and then we'll continue with the analysis. Okay, so that's just a short intro. But that's okay, we'll leave it at that and pick up with the demonstrations next time. Okay, see you later.